Uh, Good evening, sir. Dr. Amit Bhattacharya ji. Am I audible to you?
Yeah, good evening, I'm Amit Bhattacharya ji. Yeah, so are you able to hear me?
Yes, sir. You are very clearly audible.
Okay, so I will try and share my presentation first and let me see.
Yes, sir. The delegates are still in the process of joining, and
Yeah, I
we
will just,
still have 5 minutes.
yeah,
Yes, you
sure.
can.
I
You
will,
can. You can check your slides, and you can just check whether
yes.
everything is fine.
Yeah,
Yes,
are you
your
able to
slide
see?
is visible. Slide is visible. First slide is visible, sir.
Let me check whether it's moving or not. Yeah, is it moving?
Yes, now it is second slide, third, fourth.
Yeah, yeah,
Yes,
sure. Okay,
slideshow is running
okay,
fine.
okay. Thank you. So you just let me know when to start. Once everybody is joined, we can start.
Yes, sir, we will start at 6 o'clock sharp.
Yeah, sure. No problem.
And there are around 125 delegates
Oh,
from
okay.
all across India.
Oh, okay. Good,
Yes,
good.
almost from every region of India, from north, east, south, west, and the central Madhya Pradesh also.
Okay, nice.
From
Nice.
from many states, we have the delegates from many states. Total
Okay,
175 delegates are registered for this FDP, and on
okay,
an average, we are able to see attendance of 125 delegates. They are generally
okay,
present during this FDP.
okay. So your college is located in Gurdaspur, is it?
Sir, Dr. Sarabjit Singh Sidhu, he is the co-coordinator of this FDP. His college and
Okay,
university is in Gurdaspur.
okay,
My name is Shankar Sehgal. I am professor and head of mechanical engineering department at Punjab University, Chandigarh. It is based in
okay.
Chandigarh.
Ah,
Yes.
sure. Yeah,
Chandigarh
okay.
is the most well-planned city of India, sir.
Yeah, I have been to Chandigarh. I've gone to Himachal via Chandigarh and all. So yes, I've been. It's a very nice city. Yes. I've seen that.
सर आप कभी भी आइए तो हमारा यूनिवर्सिटी का गेस्ट हाउस है, यहाँ पे रुकिए. वी हैव अ ब्यूटीफुल कैंपस एट चंडीगढ़.
Okay. Yeah, I've not been to your university, but Chandigarh, yes, I've been there. To Chandigarh airport is also very nice, quite
यस सर.
green and all. Yeah, sure.
पंजाब यूनिवर्सिटी इट वाज एस्टैब्लिश्ड इन 1882 सर,
Yeah, it's a very famous
ड्यूरिंग द
university
ब्रिटिश
because
इरा.
I think my boss, Dr. Gogia, I think graduated from there, and then he then went on to IT Kanpur, and then Dr. Gogia was my head in the titanium alloy group in DMRL. So he's I think from Punjab University. Yeah. So otherwise, I'm not an expert on biomedical, but I am I am more on titanium alloys and that also for aerospace. So I've been interacting with Sarabjit because he wanted materials and all. So that is how we connected.
यस सर.
Mm.
Sir, we can, I think, now start the session. I will first make a formal introduction, and then we can proceed with the session, sir.
Sure. No issue.
My research scholar Sony Slot has also joined. Let me make him also as co-host. Delegates have his number. It is there in the WhatsApp group also. And if you face any difficulty during the meeting, so delegates can contact him directly also. A very good evening to all. Sir, shall I proceed further?
Yeah, sure, no issues.
Thank you. Very good evening to all, and welcome to this ATAL AICT sponsored online FDP. I'm Shankar Sehgal, professor from Punjab University, UIT, University Institute of Engineering and Technology, Punjab University, Chandigarh. It is my proud privilege to introduce the resource person, eminent speaker of today's session, Dr. Amit Bhattacharya. Namaskar, sir, and welcome to this FDP. He is uh, uh, he is a former scientist H and associate director, Defense Metallurgical Research Laboratory, DMRL, Hyderabad. Uh, and a career spanning more than 6 years, which is, I think, more than age of many of the delegates also. And his career has been in the field of metallurgical engineering, consisting of industrial metallurgy, teaching and research development in various organizations. He completed his BTech in metallurgy engineering in 1987 from Indian Institute of Technology, Kanpur, and subsequently did his MTech and then PhD from the same institute, that is IIT Kanpur. Started his career in Silicon Steel Mill of Raulkela Steel Plant, SAIL SAIL, in the production of CRGO and CRNO electrical steels, then moved to Asia Brown Brewery, Vadodara, at their corporate R&D center, where he was involved in failure analysis and vendor development, and subsequently taught the degree engineering students of Army at College of Military Engineering, Pune, on a DRDO posting. Since May 1997, he has been associated with the Defense Metallurgical Research Laboratory, Hyderabad, India, and was involved in R&D of titanium alloys, mainly for aircraft structural and aero engine application, and is also recipient of several awards. He also served as a postdoctoral fellow at the Ohio State University, Columbus, USA, where he worked on a Federal Aviation Administration FAA funded project and looked at the effect of microtexture on dwell fatigue of near alpha titanium alloys from the year 2007 to 2009. He also taught courses in IIT Kanpur as an adjunct faculty for 1 year in the department of MSc. He has co-guided about 4 PhD and a few MTech students at various institutes. He has more than 70 publications that includes peer-reviewed journals, technical reports, and 2 book chapters on titanium alloys in aerospace materials and material technologies, Volume 1, 2017 Springer. That is by Indian Institute of Metals, IIM series. He is the chairman of the Gas Turbine Material and Processes, Bulk Materials Project Assessment and Review Committee that grants and reviews projects to various institutions related to development of materials and processes for high temperature gas turbine applications under the Aeronautical Research and Development Board of DRDO. Before superannuation in August 2024, he served as an associate director of DMRL and was overseeing the technical activities of several groups of DMRL working in various areas and also overseeing the work of the administration of the laboratory. He has been the project leader of several aeronautical development agency, Bangalore funded projects, uh, indigenous development of a high strength beta titanium alloy, and for structural weight reduction in Tejas, and indigenous development of high temperature beta titanium alloy, cold roll sheets, and presently the ongoing project, indigenous development of titanium alloys and associated manufacturing technologies for advanced medium combat aircraft. He was involved as a titanium expert member in several projects of Navy and titanium armor, etc. He has won several awards, namely Agni Award 2007, a team award for contributions in development of indigenous titanium technology for self-reliance, two Best Presentation Awards in ATM IIM, Engineer of the Year Award 2015 by Institution of Engineers, Telangana Government, and DRDO Laboratory Award Scientist of the Year 2015, DRDO Scientist of the Year 2021, and has been made the Fellow of Indian Institute of Metals, that is IIM. He is also a reviewer of several international highly impact factor journals, namely JMOD, MetTrans, and MSc Journal of Alloys and Compounds, Filmag Letters, Trans, IIM, etc. He is also a member of several review boards, namely GITA, ARDB, DRDO, GTMAP, DRDO, etc. So, we will really be benefited to have a great speaker, eminent speaker with us. Thank you, sir, for sparing your precious time and for acceding to our request to be available for this online FDP. And I hope with your great vision and with your inspirational lecture on the titanium alloys, introduction, classification, applications, and biomedical alloys, the all the delegates and as well as the organizing team will also be benefited. Thank you so much, sir.
Thank you, Professor Saigal, for a nice and elaborate introduction. So, can I start now?
Yes, sir. Yes, yes.
Okay, okay. Thank you
Please,
very
sir.
much.
Thank you, sir.
So, good evening to you all. In the beginning, I just want to say that I'm not a biomedical alloys expert, but certainly know a few things about titanium alloys. So mostly for aerospace application, but nonetheless, I understand the biomedical alloys also. I've been tinkering with them for some time, and Professor Sarabjit has been coming to our labs a few times. He has visited and he has done good work. The topic of today's presentation now is titanium alloys, introduction, classification, application, and also biomedical alloys. Uh, so, just a sec. Yeah. So this is how I have structured my talk. First, I'll briefly introduce and talk about classification of various alloys like alpha plus beta alloys, and also near alpha high temperature titanium alloys. Beta alloys, again, which are the new, there are alloys which are used in biomedicals also. Then talk about briefly about titanium aluminides, because in our lab, a lot of work has been done on this. Then talk about shape memory alloys which are relevant to biomedical application, and also finally biomedical application, and please feel free to ask anything. I hope I'll be able to answer your queries, or you can ask in the end also, whatever you want to, whatever you have in mind, or whatever you have not understood. uh, Basically, titanium has got two principal virtues: high strength to weight ratio and corrosion resistance. Now, because of that, it finds applications in various fields primarily aerospace, airframe, engine components, marine, chemical, and biomedical applications. And there are other specialist applications like in medical and specialist applications, even in body jewelry, etc., which in advanced countries is very much there. Might not be in India because India, we have a lot of love for gold. So, but nonetheless, it does have, and also in sports equipment, etc. So now, as far as the alloying element, yeah,
Sir,
yeah,
am I
sure.
audible?
Yes, yes.
Your slide is flickering. I mean,
Flickering is.
brightness is varying, sometimes increasing, decreasing.
Oh,
It
oh,
is flickering.
okay. Okay. Let me see. Maybe my connection has become slightly.
Screen brightness is varying a lot. Now it seems to be stable.
Okay.
Now it is stable. So,
Okay.
but it is not
Uh,
in the slideshow mode now.
yeah. Now is it okay? Is it okay now?
Uh, Let me ask my research scholar Sony, are you there?
Yes, good evening, sir. So
Good
my
evening,
voice is
Sony.
audible?
Yes, you are audible. ये क्या मेरी तरफ से ही हो रहा है? मुझे अपनी स्क्रीन पे लग
No,
रहा है या
sir,
आपको भी लग रहा है वो?
it has decreased as earlier, but it is still continue.
Yes, some flickering like situation is
Yes,
there, right? Sometimes the
something
brightness is
is,
very high, then brightness is very dim.
yes, sir. Something
Okay.
is there at the end of this, Dr. Amit, sir.
Okay. And now maybe my internet connection, I don't know.
So try to increase brightness of your laptop, please.
Yeah, sure. Try and do that. Is it bright now?
Sir, now it is okay, sir.
Okay.
Yes,
Okay.
sir.
Thank you.
Okay,
Thank
sir. Okay, sir,
Yes,
it
sir.
is
Okay.
fine now. Thank
Okay.
you.
Okay. Okay.
Thank you, sir.
Sure. Sorry for that. Yeah. So as far as alloying elements are concerned, the elements that alloy with titanium, there are basically two categories. One is the alpha stabilizers, which only are few commonly nitrogen, oxygen, and aluminium. And if you see the part of the phase diagram, if you add more and more of alpha stabilizer, what it does, this line, this is called a beta transverse line. So that increases, the temperature keeps increasing. So it basically stabilizes this alpha phase region in the phase diagram. So that is why they are called alpha stabilizers. Now, as far as beta stabilizer goes, these are the elements. There are two types, beta isomorphous and beta eutectoid. And beta isomorphous elements are vanadium, moly, niobium, etc. And beta eutectoid are iron, manganese, nickel, etc., etc. And hydrogen is also one of them. Now, what addition of beta stabilizer does is, as you see, this temperature line, which is called the beta transverse line, it's a very important line as far as titanium alloys are concerned, it decreases in temperature as you go on increasing the amount of beta stabilizers. So basically the beta region or the beta phase field region increases. So same thing happens. This is a eutectoid. This is a isomorphous phase diagram that is there. Okay, and then there are certain elements which are neutral, like tin and zirconium. These are required in high temperature titanium alloys, and they don't have any effect on these beta transverse lines, so that is why they are called neutral elements. Now this pseudo-binary phase diagram shows the classification of conventional titanium alloys. Now on the y-axis you have temperature, on the x-axis you have what is known as beta stabilizer concentration. And beta stabilizer concentration is measured in terms of an empirical formula which is known as Molly equivalent. And so it gives you the measure of beta stability. So now what you do is you plug in this weight percentages of the elements that you have in the alloy in this formula, and you get a number which is known as moly equivalent. And higher that number, more alloy is beta stabilized. Now, similarly, for alpha phase stability, you have an empirical formula which is known as aluminium equivalent. So these are the elements which stabilize uh, the alpha phase. So you plug in the weight percentage of this. In this, tin and zirconium, if you see, are also there, although neutral, but it does affect the alpha phase. So and the gaseous elements, oxygen, carbon, and nitrogen are there. So this again, you get a number, and it tells you how much an alloy is, what is the how much is the alloy alpha stabilized. There is also a criteria, this number when it is greater than 1, greater than 9. So this 9 this is called a Rosenberg criteria. It is important because if you exceed this number 9 in these elements, then you start precipitating a ordered phase which is known as alpha 2, and that embrittles or increases the strength. So that is about the alloying elements. Now, if you come back to this phase diagram, you have what you know is alpha phase, then your big region, which is alpha plus beta region, and then you have beta region here. This temperature, as I told you, is this line is known as a beta transist line for titanium alloy. And it's a very important temperature because most of the heat treatments, etc., are done around this, above it, or below it. And the whole processing is done around this line. That is why you will see whenever you buy a titanium alloy, the beta transist temperature of that alloy will always be specified. So now coming to the classification, there is a classification of conventional titanium alloys. I will tell you what are non-conventional. They are basically intermetallics. So we'll just briefly see that. So on the extreme left-hand side, you have a uh, single phase alpha region. Alpha has got a hexagonal close packed structure. Now, so this is the region of alpha alloys. So alpha alloys are single phase. You cannot increase their strength by heat treatment. Okay. We'll see what are these pictorial and what are their usages. Then you come into the region of alpha plus beta alloys. Now you are seeing a dotted line, which is a martensite start line. So in titanium alloys also similar to steel, you have martensite. Although titanium martensite are not as strengthening as in steel because of there is not much distortion that happens in the crystal structure. So this is a martensite start line. So the alpha plus beta category has one of the most famous titanium alloys, Ti6 aluminum 4 vanadium, and the 50% of the world titanium alloy production is of this alloy because this is panacea for all kinds of problems, high temperature, fatigue, this, that, and also that is why, and also lots of biomedical application because this is a very used alloy worldwide. So that belongs to this category. Now, towards the left-hand side of this region, that is alpha, what you have the classic high temperature alloys, and the region is known as near alpha alloys, which we'll discuss briefly. It belongs to this region of the pseudo-binary phase diagram. Then, once you cross this martensitic start line, what happens is if you do a beta heat treatment of this alloy and then quench it, you should be able to retain the beta phase. Otherwise, all the other alloys have the alpha plus beta phase and all. So it is possible to retain this beta phase, which has got a BCC structure. And then when you age, you get fine alpha precipitation, and that increases the strength. So all the beta alloys or metastable beta alloys are for strength kind of application, like landing gear of aircrafts and things like that. So now this is a critical composition because beyond this is what you are having is beta alloys. Beta alloys are again very important as far as biomedics are concerned because new alloys are in this region because they have lower moduluses and they are going towards the modulus of the bone, which is many of the aims of biomedical alloy development. Now here is the HCP structure. You have 6 atoms on the, this is called a basal plane, this and this, and then 3 atoms here. I'm not showing you the atoms because here we are talking about the slip planes. Now, the titanium has got C by A ratio, which is less than 1.62, which is the ideal C by A ratio for a hexagonal structure. And because of that, there are other than basal, there are other slip planes which come into play. Slip planes are important because when you talk of deformation of the material. So you have a basal plane, which is a close packed plane, and you have a prismatic plane. This is called a 10 bar 10 is a prismatic plane. And these two planes are called uh, uh, pyramidal plane. The deformation on this basal and prismatic is very easy, but on this plane it is very difficult. So the stress requirement for these planes are higher. So slip takes place in this. This is one of the close pack direction 112 bar 0, and the plane basal plane is 002, and this is 10 bar 1 0. Again, this also has got a 112 bar 0 direction. This has got a C plus A slip. I'll not go into too much of detail. And 112 bar 3 is the I always talk about this because ultimately the mechanical properties are affected by this crystal structure and the deformation and all that kind of stuff. In order to understand those, these fine details are necessary. Now, in titanium alloys, most of the time, what we are doing, we are either transforming alpha to beta or beta to alpha. Convention in conventional titanium alloys. There are other phases which are there, but these two are very, very important. So what is happening? This, if you are heating from alpha to beta, then from alpha HCP, you transform to beta BCC. BCC is body-centered cubic with an atom at the center of the cuboid. So so O2, as I told you, is the close packed plane of HCP. Similarly, this plane, 110001 or 110 type of plane, is a close packed plane for BCC. There are 6 planes in a cube. Now, most of the time, these transformations happen, and the what happens is when the transformation happens, this plane, this basal plane, maps onto this plane, and that is what is shown in this picture here. This is the basal plane, and this is the close packed plane of the cube. And so this transfer, this there is. So what happens is there is some relationship, orientation relationship happens. That is 001 of 0001 of alpha maps onto 110 of beta, and this direction to 1 of alpha maps onto 111 direction of beta. And so what happens is 6 planes of 110 and with 2 directions lead to 12 kinds of variants in titanium alloy. That is why you see a very geometric pattern in the microstructure of titanium alloy, and it is it is known as Burgess orientation relationship. Okay, this is very, very important because it affects the mechanical properties again, and you can play with the microstructure and so on. And the titanium alloy microstructure is slightly complex, but once you understand, there is no issue. The other important point about titanium is the hexagonal structure, the alpha phase, has got varying elastic modulus. I mean, depending on in which direction are you talking about. In the C-axis direction, if you talk, it will be more than 140 GPa. But if you talk of other directions, you can see it reduces up to 100 GPa. So there is a huge variation, and that is one of the reasons you get texture in titanium alloys. The other important here, again, in the next diagram, what we have plotted is this is an Arrhenius plot of self-diffusion of titanium, and various elements are plotted. It is 1 by T, 10 to the power 3 divided by 1 by T. Now, this is the beta transverse line, this dash line. On the right hand side, you have alpha phase. On the left hand side, you have the beta phase. And you can see the diffusivities in alpha is lower as compared to in beta. In beta, the diffusivity is higher. Primarily, it is higher temperature, and also BCC is a open kind of crystal structure as compared to alpha, which is a close packed structure. This has got implication in heat treatment. That is why I'm just pointing this out to you. The other important aspect is I was showing you these different planes, and this is the on the y-axis is On the y-axis, you have critical resolved shear stress, and this is for Ti6Al crystal. And this is Ti6Al is very common to all the high temperature titanium. So if you focus on this CRSS, you can see the CRSS of prismatic is the lowest. That is the stress required to start deformation in the prismatic plane is the lowest. After that is basal, and this is for C plus A. There is a huge difference in CRSS. So it is very difficult to deform in this C plus A slip or the pyramidal slip, or to activate the pyramidal slip. This again has got implication in the mechanical properties. That is why I'm just pointing out and giving you the basics of this. So now we go on to alpha titanium alloys, the category. So these were developed for lower strength applications. And requiring moderate strength, etc. And and they also are used for corrosion resistant applications. And there are currently about 16 grades of CP titanium is commercial purity titanium, and alpha titanium alloys. And these are, as I told you, non-heat treatable, and this command about 1/3 of the total titanium world market today. It is somehow got. So these are the commercial grades of CP titanium, and what you can see is on the right hand side is the yield strength, and here is oxygen is a strengthener also in titanium alloy, and if you add more and more, it's strengthened, but too much of it is not good because it also causes brittleness in the alloys. So as you go into various grades, the oxygen levels are higher, and you can see the strength levels also get higher. Then there are certain grades which are used for corrosion resistance application, like for electrowinning of metals or electrodes of in electrolytic cells. So you have additions of palladium and lithium and all that, and these are the strength level. The other important alloy in this group, and can be in the other group also, but this is not heat treatable. It is called half alloy. This is half the composition of Ti6Al4 vanadium. That is why it is called a half alloy. And this is the strength level, and this is used for making tubes, hydraulic tubes, which are used extensively in aircrafts for carrying hydraulic liquid. Now, this is briefly how the alpha titanium alloys are processed. The ingot breakdown and homogenization, everything happens in the below the alpha transverse, in the alpha region. Deformation, recrystallization, everything is happening in the alpha uh, phase field region only. The whole processing is in alpha region. Okay. Now this is a typical microstructure. This is a single phase material. That is why you are almost not seeing grain boundaries. So these are grain boundaries. Now in this is a microstructure of Ti5Al 2.510, and there is certain amount of beta at the boundaries. Beta is sometimes added, that is iron is added, which precipitates that beta phase, and this controls the grain boundary because there are no other phases which are present. A certain amount of beta elements are added just to precipitate some amount of beta and control the grain sizes. Again, biomedical, how is it related? Is earlier alloys were, and still now this commercial purity titanium alloys, and you can see the strength levels are such they can compete with aluminum alloys straight away. This is another tube and shell heat exchanger application. CP titanium is used a lot for heat exchanger applications, etc. Then this is the example of a half alloy. This is the microstructure of a indigenous produced tube, and this is the microstructure of imported tube. We can see the imported tube microstructure is pretty fine. The bright particles that you see is of beta phase, and rest is alpha. So you can see the kilometers of it is used in LCA and other, and various diameters are used. And this is just a picture where it is used in the aircraft application. So the processing is basically you take a melt and produce bars or billets, bore it, and then carry out hot extrusion, series of cold pilgering, annealing, pickling, and then ultimately qualification certification is required if you want to use it for a aircraft application. Now, and then I'll switch over to alpha plus beta titanium alloys. Now, these are just example of some alpha plus beta titanium alloys. You have Ti64 with higher amounts of oxygen, that is 2000 ppm of oxygen, and you also have a ELI grade. ELI means extra low interstitial. The oxygen levels are lower. This is used for if you want to do a lot of deformation. This is a grade, and superplastic farming and all, you should use this grade. Then these are near alpha high temperature titanium alloy 6242, 6242. These elements are, as you can see, the aluminium is around 6 aluminium is used, and there are other elements are there. And then silicon is also used in most of the high temperature titanium alloys because it improves the creep property. And there are other alloys, Ti81, IMI 685, etc. etc. Yeah, this is the picture of a yeah, high bypass ratio aero engine. So titanium is used in the fan part. You can have composite blades also. Then in the compressor section also, near alpha high temperature titanium alloys are used, and also in here. And then nowadays in GE engine, you have aluminides being used instead of nickel-based superalloys in these last two turbine sections of the aero engine. Then the rest of the high temperature parts are made of mostly nickel based, and also sometimes the tail plug is also made of titanium. Yeah, this is how the alpha plus beta alloys are processed. The initial ingot breakdown happens high in the beta region. This is the beta transverse line, that dashed line. So because the flow stresses are lower, because you require a lot of force, because the ingot sizes are big, they are more than 650 mm dia. So initial homogenization, that is chemical homogenization, also happens by soaking in beta phase because the diffusivities are higher. So you deform, firstly break down the ingot high up in the beta, then you can carry out deformation in the beta region or alpha plus beta region, depending on what type of microstructures are you're looking at. And then final recrystallization and annealing mostly happens in alpha plus beta region, in case of alpha plus beta alloys. The other important aspect about titanium alloys is, yeah, I will show you the microstructure. If you cool from beta, you get very big grains. Now you have lats of alpha and beta alternating. It is like perlite and steels if you are used to. So here I'm just showing you the lats alpha and beta, alpha and beta. So what happens in order to control the grain size, you have to convert the alpha that is there, fascicular alpha, to globular alpha, and that sits on the grain boundaries and controls the grain size of beta size. So certain amount of deformation when you give these alpha lats, in the alpha lats, slip bands form. Then what happens? The beta penetrates the alpha, which is shown here in the picture of the microstructure, beta penetrating the alpha. Alpha is the black one, and then rotation, recrystallization, and of alpha happens, and that globular alpha forms, and it basically controls the gains. I'll show you them in the microstructure. These are the typical microstructures that you get in titanium alloy. The first on the top, this one is when you cool from beta. This is called a transformed beta microstructure or a lamellar structure. You can see lamellar. But the other thing that you can see are, you can see different colonies. So these are alternate lats of alpha and beta. Bright is beta and the dark one is alpha. And the other thing that you also can see in the microstructure, there is a lot of grain boundary alpha. Now this is like precipitate free zone, and it impairs the mechanical properties. So you want to, the whole processing, one of the processing is one of the processing points is to take care of this grain boundary alpha. You should not have grain boundary alpha. And as I told you, due to the Burgess orientation relationship, you see different colonies of alpha, and that is where the complexity of titanium alloy lies, because this whole thing can serve as a grain, or these sub these alpha colonies can also act as sub grains and things like that. So these are called colonies. So this is called a lamellar structure. This happens when you cool the alloy from a beta phase field. This is Ti6 Ti64 Ti6Al4b microstructure when you cool from beta phase. Now, the microstructure on the right is called the equiaxed microstructure, and you can see the dark colored alpha and beta on the boundaries. This kind of microstructure is good for superplastic formation, or when you want to do a superplastic formation of certain components, etc. This kind of microstructure you will get if you do a lot of deformation in the alpha plus beta region of the alloy and then cool slowly in the furnace. If you cool slightly faster, then you get what is known as a bimodal microstructure, which is shown here. This is a typical microstructure that you have in turbine blades and compressor blades and all of titanium alloys. So what has happened is this is the bright things are alpha. This is a optical. These are the electron microscopy pictures. So that is why you have inversion of this. So this bright globular things are alpha. As compared to the top, you can see the grain size has become much finer. And depending on the cooling rate, you can have a finer structure or a slightly coarser structure. Now, this again, microstructure is important because you are trying to optimize the mechanical properties. This kind of microstructure is very good for creep, fracture toughness, but this kind of microstructure below is bimodal microstructure, very good for fatigue kind of applications. So depending on what is your application, you can choose the microstructure and thereby impart deformation accordingly. Here I'm just showing you the schematic of strength versus tensile ductility. At a particular yield strength, the equiax structure has got a higher ductility as compared to a lamellar structure. A lamellar structure has got a lower ductility as compared to a equiax structure. But if you compare, if you plot fracture toughness versus yield strength, the laminar structure has got generally a higher fracture toughness at a given strength. Equiax structure does not have that kind of, and laminar structure also has got uh, better creep properties. So depending on what is your application, you can design your microstructure. Now, what is the principle of improving creep strength? Now, in high temperature near alpha titanium alloys, you want to restrict the amount of beta phase, less than 10%. Now, because beta phase has got higher diffusivity and that basically impairs creep property. So, you decrease beta stabilizer content and add the neutral elements like tin and zirconia. You add tin and that combines with aluminium to form intermetallic, which strengthen the alpha layer. Then replace higher diffusivity beta stabilizers like vanadium with slower diffusing species like moly, niobium, etc. The other important point about titanium alloys is you have to have very low amounts of iron and nickel because this causes very fast diffusion, which is called anomalous diffusion and impairs the creep property. And as I told, the silicon is always added in high temperature titanium alloys because it improves the creep properties. And the other one is just anneal, which is done for a particular annealing. It improves the creep properties. So I will just briefly talk about the processing of this silicon bearing high temperature titanium near alpha titanium alloys. There you can see various lines, uh, dotted lines. First is the beta transers, then Ti silicide solvers, and then Ti3Al solvers. So you can see the ingot breakdown homogenization happens in the beta phase, high up in the beta phase. Then most of the deformation happens in the alpha plus beta region, but above these two solvers, because these two precipitates are very brittle. So once you form, the material will start cracking. So that is why the deformation, etc., is given above these solvers, and the final heat treatment is done below the solvers so that you get precipitates out, and then that improves the property. Just to show you, this is a transform beta microstructure, that is alpha, beta, alpha. This is the same picture. And in near alpha titanium alloys, this beta is discontinuous as compared to Ti64. In Ti64, this line will be full of beta. But here you have intermittent beta. So slip can happen from alpha to through beta to another alpha grain. So that is why this silicon is added, which forms silicides and basically prevents slip transfer from one alpha lat to other alpha lat, thereby improving creep properties. Other important point I was making is that very low amounts of iron and nickel you can see impairs the creep properties. Here the same alloy melted with different amount of very small amount of iron and nickel. You can see the top alloy DM834HF is melted, has got 230 ppm of iron and 90 ppm of nickel. Whereas this one has got 65 ppm and 20 ppm. And these two were creep tested at 873K and these tests, and you can see the jump in creep. So because of higher diffusion in the alloy containing higher amounts of iron and nickel, this happens. So you need to restrict these iron and nickel amounts in the high temperature titanium alloy. Again, just showing you that lamellar structure gives you a better creep property as compared to bimodal microstructure. But in certain applications, like compressor blades and all, you require both creep and fatigue. So that is why we do a optimized bimodal kind of microstructure, which is this. You have primary alpha and then transform beta as compared to a lamellar microstructure. So all the blades, etc., which have rotating parts in an aero engine are made to have this kind of bimodal microstructure. So you compromise slightly on creep, but the fatigue improves. These are the certain components which were done for Kaveri engine program by DMRL, discs, blades, connecting rod, rings, etc. But it had got a problem of some fatigue because of texture issues, but I'm not going into details about that because this is not the forum. So if somebody is interested, we can discuss that. And the other thing that happens is when you there is something known as dwell fatigue debit. That is when you increase the load and hold it for a certain amount of time, the fatigue life as well as this kind of dwell fatigue becomes lower. So these are two diameters that were produced. This is the yield strength, and you can see the continuous fatigue life are much higher for the rod, which was deformed quite a lot to make 25 mm versus 250 mm billets. And if you divide this continuous cycle by number of dwell cycles, you get what is known as dwell debit. The dwell debit is also higher because this is because of texture, not nothing else. But we are not going into too much of detail about this. I just wanted to point out here again. Abroad also, this lot of failures have happened. So that is why they had studied this very thoroughly. Still, the studies are on. They had produced material with low microtexture, high microtexture, beta forged material, and the retired impulse. Actually, the effect on mechanical properties of texture in titanium alloys has been since last 20-25 years. It has been understood. So that is why earlier material with processed had certain amount of texture, and so they had well tested. And the only point I wanted to make is that high microtexture material also shows higher life debit in the dwell fatigue region. So this was a certain part of my postdoc work. So this is part of the ring that was given. There is a slight variation in microstructure, which you can see, but nothing much. But they were giving different ultrasonic response. The idea was can we do a non-destructive evaluation of this micro texture that affects dwell fatigue. And when you look at microtexture, you can see these different colors are means that they are oriented differently. Crystal structure has got different orientation. This has got very high size of microtexture region. This has comparatively lower. This is a very randomized microstructure. This is the microtexture. So this is the kind of microtexture that you want to get for good mechanical property. And this has got microtexture like elongated stringers in certain directions. Value see the material. This is attenuation versus microtexture region size, and it plots the higher the attenuation, the microtexture region size is higher. So in this kind of material, if we send ultrasonic signal from left to right versus top to bottom, this is the case, the ultrasonic attenuation degree. So the point being that by doing ultrasonic NDT, you can sort out the material or material which has got high microtexture versus low micro. So texture is again a very important point when you are processing the titanium alloy. Now I will briefly talk about beta titanium alloys, which are for strength applications. In beta titanium alloys, basically you add lot of beta stabilizing element so that you can, when you quench, you can retain the single phase beta. There is nothing else. But nonetheless, there is certain other phases which form, which is known as omega phase. So it is uh, uh, technically not correct that is a single phase, but nonetheless we ignore this and go ahead. These are the elements which are added to stabilize the beta phase. These are beta stabilizers, and you can see the iron, cobalt, nickel, manganese. These are very strong beta stabilizers. That is, you add small amount of it, and you can retain the beta phase in the titanium alloys. This is again a pseudo-binary phase diagram of. So as I told you, the beta phase starts from here. These were some of the alloys that we had developed for aircraft structural application. This is the region of omega plus beta, and there are other beta prime plus beta. So generally, these happen around 400, 450 degrees centigrade. So when you age in beta alloys, you have to be careful. You should age above this, otherwise you get embrittling effect of omega, which is a hexagonal phase and embrittling. These are certain commercial beta alloys that are there. SP700 is a Japanese alloy. Then 5553 is used for aircraft application, 1023 also, and 1021S also. And you can see the beta transist temperatures of these alloys are much lower as compared to near alpha high temperature or alpha beta alloys like Ti6Al4B, because you have a lot of beta stabilizing elements in them, and aluminium amount is comparatively lower. So what are they used for? They are used for high strength application, fastener, helicopter rotors, landing gears, low modulus application like springs, then medium strength application, aircraft structure. They are used in oil field application, and also beta alloys are ones which have got lower modulus, so they are used as orthopedic implants, particularly hips, etc. We'll talk about it. These are the certain spring kind of applications in aircrafts. Beta alloys are used. Again, big landing gear parts. You can see this. This is called a truck beam. This is also forged from a alloy 1023, which we had indigenized and all. And why beta alloys like 1023 are used is because if you, this is flow stress versus temperature. This has got the lowest flow stresses. So when you do a forging, closed die forging, this takes the shape complex. This can take complex shape. That is why they are quite good. So this is an example of a helicopter rotor, which is made of 1023. So this is a Westland helicopter. This is the 1023 that we had indigenized for the LCA program, 100 dia and 60 dia bars. This is the microstructure. You have primary alpha and they're very fine beta within the transform beta there. And this is one of the components. This is called a dropping. This is part of the landing gear of the LCA. This was made and replaced the nickel chrome moly steel, and that causes weight reduction in the aircraft. Weight reduction is a big thing in aircraft engine as well as the structure. This blue color which you see is because of anodizing, because titanium has got a bad wear property, not very good wear property. So you have to put an oxide coating on that to improve the wear properties. This is again a sheet application, another alloy, 15 moly niobium called beta 21S. This is one of the applications. This was also indigenized. This is although beta alloys are not used for high temperature application, but this alloy particularly can be used for high temperature applications. You can make sheets, you can make foils, etc. for different kinds of applications. Other alloy that is being utilized is 5553. This has got a higher hardenability, and this is a variation of a Russian alloy VT22. These are the two microstructures which are there: beta treated and aged, alpha beta treated and aged, and you can see the primary alpha dark colored and very fine alpha precipitation within the beta. So a lot of studies were done, and this was the has got good combination of strength and ductility, 5553. And again, the texture is very, very important, but I'm not going into the details of this. So just to show you that texture again is very important in these kinds of titanium alloys. This again the usage of 5553. You can see the bogey beam, the other things, and here the comparison is made between steel, various properties, 5553 versus 64. So you can see why 5553 is good as compared to steel. It does not have that much of strength, but it compares, but it causes a lot of weight reduction, which is there. Now, titanium aluminides are basically intermetallics. When you increase the aluminum content, you start precipitating phases like Ti3L, which is known as alpha 2. It's got a hexagonal structure, and if you still keep increasing aluminum content, you again precipitate another phase, which is known as a gamma phase, which is known as TIL. So these are all ordered structures. So these alloys are very, very brittle, but they are very, very important nowadays because these are very good for high temperature application. DMRL had worked on Ti3L based intermetallics, as well as TiAl based intermetallics is now being worked on. They are important because density is lower, elastic modulus is higher. They have got good oxidation resistance. As you can see here, third generation, second generation gamma TI near alpha titanium. It's got a much better oxidation resistance, and people are studying this thoroughly because they want to. GE has used it in one of the GenX engine, and it has led to around 100 kgs weight reduction. So these are very attractive properties of TIL, basal or specific modulus, specific 1000 hour rupture strength, etc. But the problem is the ductility is very, very low. So design philosophy has to change, etc. There is also a design, how you design these gamma aluminides, which are there. There are various elements which you add for ductility, for high temperature properties, for refining the grain size. Those are kind of known, but it's got a complex phase diagram. So that leads to a lot of metallurgical aspects, a lot of studies where then we have identified certain alloys which has good oxidation resistance and good creep strength also. These are just to point out the levels of the gamma aluminide. What they do is they can retain the temperature, the strength at higher temperature. That is why they are useful. Although the room temperature strength might be low, but they retain it at high temperature. So that is why they are attractive. This is the cutup of a GenX 1B engine, in which the last two stages, the gamma aluminides have replaced the nickel-based super alloys, resulting in 100 kgs of weight reduction. You can also make high stiffness structural panels for this. We are talking about hypersonic vehicles and all. You can use them there. So these are certain of the uses. So I will now switch over to the business end of this talk. So first we will talk about shape memory alloys. Now in shape memory alloys, basically there are two things, concepts. One is super elasticity and the other is shape memory. Now, superelasticity occurs when materials like TiNi, which is called nitinol, is mechanically deformed above its austenite finish temperature. So what happens is this causes some stress-induced phase transition from austenite to martensite. Since the martensite is not stable above the AF or the austenite finish temperature, so whenever the stress is removed, you get back the strain, and so that is why it is called super elasticity. So recoverable strains of the order of 8% you can get. So that is what is super elasticity. So the other effect that you get is known as shape memory. So this is the ability of a alloy or a metal to remember its shape. Basically, it exists in two crystal structures, one at a high temperature and the other at lower temperature. So just by temperature change, you can get these two crystal structure, and thereby you can get out a lot of strain, and it can remember the structure that is there. So it can remember the form it was there earlier. So that is how it That is what is the basis of shape memory effect. Basically, there is no macroscopic deformation which happens, but because of twinning and retwinning of crystal plane, this shape memory effects happen. So now, if you look at this transformation, so here you have one crystal structure known as martensite, the other is austenite. Here are several temperature austenite formation, austenite start, martensite start, and martensite finish. So here is martensite, here is temperature. So now for shape memory effect, it happens between MS and MF. Okay, so basically the crystal is transforming between these two structures. That is why it is able to, just by change of temperature, it can change from one to the other, and you can remember the shape. And super elasticity happens beyond this. So temperature which is above the austenite finish temperature, because you deform and form the martensite, but as soon as you remove the stress, it comes back to martensite. So you get a lot of elasticity. So it is called super elasticity. These are certain titanium-based, nickel-based shape memory alloys, and these are the MS, MF, AS, AF temperatures. So depending on the application, you can choose your alloy and then tail it. But let me tell you, because we have some experience in shape memory alloy, it is very, very composition sensitive. Slight variation in composition, these transformation temperatures change. But nonetheless, they are very widely used and they are quite costly also. So they are used in biomedical applications quite a lot. Here are certain of the aero applications: smart wing, SMA torque tube, F-15 inlet cowl, and then also you have Boeing using it as a variable geometry chevron, which is used to control the noise of an aero engine, etc. These are you can have flexible hinges. You can deploy the antennas in this space. You can have couplings. These are used again in aircraft. You just do change in temperature, the transformation happens, and it grips the pipes that it is holding. The couplings can hold the pipes, join the pipes, etc. Spectacles, and it's also used in golf clubs, etc., etc. So these are the various non-medical applications. So I will talk about just medical applications after this to show you the pictures. So in biomedical applications, what are we looking at? We are looking at corrosion resistance, biocompatibility, bioadhesion, that is osseointegration, and certain amount of mechanical properties, because it has to have certain amount of strength, fatigue strength, etc., and processability. Obviously, availability, it has to be available at lower prices comparatively. So titanium is generally biocompatible metallic material. It resists corrosion by the body fluids, and that is why it is preferable as compared to steels and other material. And implants most of the time carry mechanical loads. So titanium alloys have got good strength, and they have very good weight to strength ratio and good fatigue properties, because you use them, load and unloading happens, so fatigue is important. And so the other point favorable about titanium is it has got lower modulus compared to steels and other alloys. So that is why it goes towards the human bone, and that is why they are widely used as implants. Now, there is a lot of new alloys which are there, are beta titanium alloys mostly. So there are basically certain alloys deformed by slip and twinning, and the others by twinning and martensite formation. So you can, depending on what you want, the sensible, etc., you can choose your alloys actually. Alloys which deform predominantly by slip show basically higher strength. Alloys which deform predominantly by twinning, so larger ductility and lower modulus. So if you want alloys to fall in the twin region, these are certain: titanium 13 NB13 ZR, titanium 12 moly 6 ZR 2 Fe, and titanium 35 NB 7 ZR 5 tantalum, etc., etc. These are certain of these alloys. Now, I will just go through the titanium alloys grade-wise usage. So as far as commercial purity titanium is concerned, CP titanium, we have seen these grades that in the introduction part I told. So increasing content of oxygen, increasing the strength. So applications are dental implants, orthopedic screws, craniofacial plates, and the key property being the biocompatibility, and but they have relatively lower strength as I've shown compared to other alloys. Then you come to alpha plus beta alloys. One of them is Ti6Al4b and Ti6Al4b ELI, extra low interstitial. This is the most widely used aerospace alloy, which I've told you, and this has also been adapted. This is one of the first alloys to be used for medical usage. So as hip stems, knee prostheses, dental implants. So, but the concern, we are going to newer alloys because they are concerned about vanadium causing cytotoxicity and also aluminium causing neurological effects. So you don't have these in the newer alloys. So firstly, vanadium and aluminium-free alloys, these were developed to avoid potential problems of cytotoxic element, that is niobium replaces vanadium, and application in orthopedic and dental implants. Then you have Ti5Al 2.5e, where Fe is replaced with vanadium. Now later, so then since aluminium was also causing problems, so we moved to metastable beta alloys, and also because the earlier alloys had got higher modulus. So beta alloys, as I told you, have got a lower modulus, and newer alloys are kind of reaching towards bone, although not reached. You can see the Ti6Al4b has got 110 GPa modulus, whereas our target model is 30 to 40 GPa. So these beta titanium alloys are much better off in that sense. So one of the alloys is T, uh, TNZT. This is the alloy. So it is used for orthopedic implant elasticity, which requires elasticity close to bone, cardiovascular stents, and the elements that are there are very highly biocompatible. Then people are also moving to surface modified porous titanium alloys. Porous Ti64 is also being talked about. Titanium alloys with bioactive hydroxy, and that has been promoting osseointegration. Then you have the shape memory alloys, which are used as orthodontic wires, etc., cardiovascular stents. But again, the problem is nickel release, which causes allergic reactions. So now people are trying to design titanium niobium and titanium moly based nickel-free shape memory alloys, which are there. Now, as far as application wise, if we go, so for orthopedic applications, you have various grades of CP titanium for bone plates, screws, then Ti6 4 ELI grade for hip stems, knee prostheses, and then other TN, TZ, low modulus, hip, knee, stems, bone plates, and also Ti35NB 7ZR5 tantalum advanced load bearing implants closer to the modulus of bone, that is lower modulus. Then dental applications, these are the alloys which are used, CP titanium, 6Al4b, and also NITI orthodontic wires that you see. Then for cardiovascular devices, CP titanium is for pacemaker and defibrillator housings. Again, shape memory, beta titanium alloys. For craniofacial, maxillofacial application, you use this kind of alloys. So nowadays you are getting porous Ti643 that is 3D printed, so you can customize the cranial plates with bone ingrowth potential, etc. etc. Then there are specialty or novel applications which are there. Shape memory alloys, the polars, additively manufactured titanium alloys, which is possible so that you can do a custom-based orthopedic implant with osseointegration. Then you can do surface modification, which is also important for that improves the bone bonding and antibacterial surfaces, which reduce the infection chances, etc. This is the timeline summary of the alloys, titanium alloys. In the earlier part, 1960s, we have commercial purity titanium. Then 70s to 80s, we saw Ti-64 being used. Then came the vanadium-free beta alloys, which are there. Then there was an advancement in the beta alloys. Then in 2000s, 2000s, we saw nickel titanium shape memory alloys. Now to 2010, all 3D printed porous titanium surface modified by bioactive coatings. Then in 2020s and all, now you can have a specific patient specific beta alloys, nickel free shape memory alloys, etc. etc. These are some of the titanium alloys and their strength level and elastic modulus and all. You can see these the beta alloys which are towards the bottom end have got much lower modulus, good strength levels, etc., and good ductility, etc. In them. Just showing you some pictures of the titanium alloys used in a biomedical application. Ti6L Part B, hip replacement, cast and rod pass, commercial purity titanium, cast dental, shape memory, orthodontic wires, Ti6L, dental screws, but then for making them, you just need a small furnace because titanium is melted in vacuum, then micro machining and coating unit, and also micro mechanical testing units to make a compact, to make a biomedical device, etc. These are again certain biomedical applications. Again, orthodontic wires I have shown you. Again, for root canal treatment, you use shape memory drills. For you use also cardiovascular devices, which are shape memory alloys. This is a Simon filter, and this is a stent, which basically again is a shape memory. You can just put it in when it is contracted and then expand it just by a slight heating and phase transformation. This again is the spinal vertebrae spacers, shape memory alloy, and also a porous shape memory alloy, artificial bone implants in the skull, etc. You can do. So that is all that I had to present. I have acknowledgements to these people uh, uh, during my development years. They have played a part, and I thank the Titanium Alloy Group members also because many of the work that I show are part of their work. And so, yeah. So, if you have any questions, please ask. I will unshare the presentation first. Yeah. Thank you all.
Thank you, sir, for such a nice, informative, and elaborative session. Audience, they can unmute their mic. If you have any query, please feel free to ask.
Yeah, anybody, if you have questions, please you can share, ask.
Good evening, sir. This is Vishakha. I'm a dentist by profession. There's no question
Okay.
from my end, but I really liked your presentation, very crisp presentation about the titanium alloys, because we use the material, but we don't know it as much. So it was really good
Yeah, yeah.
to hear from you. That just that. I got to know titanium way better than what I know early. So that is what.
Oh, okay.
Thank
Thank
you
you.
so much.
Thank you.
Thank you so much.
Dr. I would like to add here, Dr. Vishakha is also from Punjab University. We have a dental
Okay.
college here.
Okay.
Am I right, Dr. Vishakha?
Yes, sir. I'm very much there in Dental College, Punjab University. I'm there only. Yeah, we are neighbors.
Yes, yes, ma'am. Hmm. And sir, can it be processed using this microwave technique also? Uh, has Is it applicable there for processing of titanium alloys?
No microwave because these are slightly higher temperature materials. The melting point is around pure titanium melting point is around 1682. So I mean you have to use more power. So microwave is not used, but you can use laser and all, like 3D printing and all. They use lasers and all. So yes, that is used, but not microwave.
Yes, if there is any other query from audience side. Okay, sir.
Okay.
On behalf of the organizing team from Sardar Beyant Singh State University, Gurdaspur, Department of Mechanical Engineering of that university, and my own department, that is University Institute of Engineering and Technology, Punjab University, Chandigarh. And on behalf of the delegates also, I would like to thank you, sir, for taking out your precious time especially during this evening hours. It is,
Yeah.
yes,
No
because
issues.
it is definitely the time for a walk or for your personal interest. But still, you have managed to take out time for our audience, and we are really thankful to you for this. And Dr. S.S. Sidhu has also joined now. He was in a meeting today. There was an urgent meeting at his office.
Yeah.
Uh,
Yeah. Okay.
Dr. Sidhu, welcome to this session.
Thank you, sir. Today I have an urgent meeting with VC, sir, Vice Chancellor, sir.
Okay.
So that's
Okay.
why
Sure.
I'm
Sure.
not able.
Yeah. Yeah. Sure. No issues.
Uh,
Okay.
so very nice to
So,
meet you after a long time, sir.
yeah. Yeah. Virtually, at least we can meet. Yeah. Yeah.
Yes, sir.
Okay. Thank you all for having me, and thank you. Thank you very much. So I'll log off then.
Yes, sir.
Thank.
Thanks, Dr. Ramesh, sir.
Thank you, sir. The delegates are requested to please stay online, and the next session will be started at 7:30 p.m. And Professor Harpreet Singh, a renowned professor from Indian Institute of Technology, Ropar, uh, will be the resource person during that session. Please stay online, everyone. Thank you so much.
Good evening to all of you, dear participants. Please wait for some time. The next resource person will be join us within next 5 to 7 minutes. Thank you.
Dear participants, till our next resource person will join this meeting, I want to inform you that I have dropped an email to all the participants regarding our special issue on biomaterial. And if anyone is interested, he can submit his manuscript, a quality manuscript in that journal. So journal is having zero article processing charges and the impact factor is 2.9 SCA. Another journal which our team is handling and that scientific reports journal is from the publisher of Nature. Again, that journal is also writing the papers related to a biomaterial. So if anyone is interested, he can submit his manuscript. But I want to inform that the scientific report journal is having the impact factor of around 3.9, I think. But there are article processing charges. So we have floated two call for paper journals. One is Journal of Material Research and one is Scientific Report. So I think most of the participants have received that email. So you go to the journal background, what are the various thrust area that we are inviting in that. But if anyone is working on biomaterial, he can submit his paper in that journal. So I think within 5 minutes, 3, 4, 5 minutes, our expert join it and
Excuse me, sir.
please wait.
Hello. Sir, can we submit? My research work is on nanofluids. Can you submit on that also? Nanoparticle and nanofluids.
But if nanoparticles are related to somewhat to the biomaterials or biomedical applications, you can submit it. You please see the scope of that call for paper. If it is related to some sort of an biomaterials, and so you can submit it.
Okay, sir. Okay, thank you.
So here I want to.
Dr. Sidhu, I'm sorry to interrupt. Could you please repeat the name of the journal again? Scientific reports I could hear. What is the other journal?
Another journal is Journal of Material Research.
Okay, right.
It is an Springer, and I think you have received an email from my side. You can see it, the complete scope of that journal.
I checked. I couldn't find the email. That is why I asked the name Journal of Materials.
Yeah.
Right, sir.
Okay.
I'll go
No
through.
problem.
Thank you. Thank you.
Okay, thank you. So we have collaborated with IIT Delhi, and I am also handling the book series, which has been published by Springer. If anyone is interested in submitting a chapter, or if anyone is interested in submitting the proposal, so he or she can submit the proposal to write a book, and that book is related to a biomaterial also. So if you have some sort of an idea, you want to write something, some monograph or some chapters, you can submit your chapter in that also. So that book series has been handled by me as well as Arnav Chandra from AIMS, faculty member of AIMS as well as IIT Delhi. His lecture is also scheduled in this FDP. So that information I will also share with you.
Thank you, sir.
You can see on your screens, this is called paper. This is a journal of material research for journal. And the submission deadline is January 30th, 2026. And this call for paper has been handled by a professor from Brazil and one from IIT and myself. And the second journal is a scientific report journal. Manuscript to call for manuscript or call for paper in journal, then it is a very bright chance to be for the manuscript to be accepted because it has been processed fast because we have a limited time.
Hello, sir. Sir, I have not received the mail that you have just told that you sent it.
Yes, actually, I think there is a problem with your email that you have given to me because it is back to me. I will again try. I will again try from
It
some.
is, sir, it is cumail.in, not gmail.in.
Yes, yes, I have taken that mail, but I don't know. Some of the mail reverted back to me. I will try again to send you the fresh mail.
Thank you, sir. So nice, sir.
Hmm. So I think Professor Harpis sir has joined us. So before that, please allow me to give a brief introduction about Professor Harpis sir. So may I start, sir? Okay. So Dr. Harpis Singh is currently working as a professor at IIT, Indian Institute of Technology, Ropar. So after doing BE and ME in mechanical engineering, he did his PhD from Indian Institute of Technology, Roorkee in 2005. During his PhD, he worked on high temperature corrosion of superalloy and its prevention by plasma spray coatings. He has been doing extensive research work related to a thermal and cold spray based surface engineering and cold spray additive manufacturing since the year 2002. He has authored 15 book chapters and contributed more than 200 research papers in various reputed international and national journals. He has done pioneering work to explore the use of cold spraying to develop a erosion corrosion resistant coatings. He has completed and been pursuing several national international sponsored projects SRD, EPSRC, IUSSTF, GCRF, ARDB, and UKIERI. He has been doing several consultancy projects with the industry in surface engineering and additive manufacturing. He has Indian and 2 US patents to his credit, along with 3 patents under processing. He has produced 24 PhDs, wherein more are currently working under his supervision. He has also mentored more than 10 postdoc fellows. He has visited several countries including USA, UK, Netherlands, Australia, Canada, South Africa, Spain, and Germany to attend the various international conferences and as a part of academic delegation. He has also coordinated several short-term courses and delivered many exposures in various institutes in India as well as in abroad. He is a recipient of Kansai Nerolac Excellent Award for the Excellence in a Coating Research, Young Scientist Award, and Career Award for the Young Teacher, and Maharashtra State National Award for the research work done by teachers of engineering colleges in 2007. By the Society of Several Protective Coatings, Punjab Academy of Science, AICT, ISTE respectively. The government of Punjab awarded him with the Achievers Award for the year 2019 for his overall contribution as an educationist. Recent breakthrough by his group are developing 2 novel and economical technologies for surface coating and additive manufacturing using a raft practical particles as a feedstock, which are named as a grind process and chop saw printing respectively. He has also established a national facility on high pressure cold spray at IIT Ropar, which is one of its kind and has a capability of additive manufacturing in addition to the surface engineering. He is an adjunct professor at Swinburne University of Technology, Australia. He is the founder president of Indian Spray Association and vice president Society of Mechanical and Material Engineering. Sir, we are grateful for your enlightening presence in our FD on biomaterial, and we really appreciate, our team really appreciate that you spared your time to join us despite your busy schedule. So, sir, may I kindly request you to begin your lecture, please, sir.
Hello, thank you, Dr. Sadhu. Can you hear me? Hello,
Yes, but
can you
voice
hear
is
me?
little bit low.
Oh, can you hear me now?
Yes, yes.
Oh, okay, let me. Actually, I have some problem with my system. Um,
Sir, it's okay, sir. It's okay. Sir.
Okay, thank you very much, Dr. Sidhu, for this introduction. In fact, it's very embarrassing to listen to all these things. The credit basically goes to my students, of course, who have done a lot of work during the last several years, and due to which I am kind of being given the credit. And of course, it's my pleasure to be here today. And good evening to all of you who are present today. So let me share my screen before I say something else. So. Sharing time. Hello, can you see my screen now, Dr.
Yes,
Sidhu?
sir. Yes, sir. Yes, sir. We are very much clear, sir.
So yeah, it's in presentation mode now, right? and these slides are
Yes,
moving,
yes.
right? Mhm.
Yeah, yeah.
So, okay, thank you very much indeed, and good evening, all of you, once again. So today, in this on this evening, I'm going to share my experience with the cold spray based coatings for bioplant applications. Uh, so this is a work basically. You can call it a case study being done by one of my students, Dr. Avnish Kumar, uh, uh, for his PhD a few years ago. So yeah, so the title of my talk will be Experimental Investigations on Cold Spray Titanium Based Coatings for Bioimplant Applications. There were kind of some motivation behind this work, and one of them, obviously, we all know that by now, actually, this is a course on, I think, exclusively on your biomaterials. So I can understand that there is a lot of you know understanding now among the audience that this is an area which is of growing importance, and even from our commercial point of view. So we can see that this medical devices and if I talk particularly about orthopedic devices, the market is ever growing. We can see it even if you talk about Indian scenarios. We are touching, say, almost $1 billion, and of course, global market is much much bigger uh, with regard to this orthopedic devices, which is touching something of 60, and now we are aiming at something of 100 billion USD by 2029 or so. So if you can see a lot of further, sub classifications where or the how market is catching up in different segments like spine, knee replacement, hip replacement, and so on. So we can see that this market is ever growing. Um, Now, what are the biome plants? So we know that basically when we have to replace some of our, natural parts by some of the, artificial kind of components, then we call them, biome plants. So especially we have now a number of examples around us. Uh, uh, in terms of a knee replacement, and sometimes due to accidents, we have to replace some of the, missing um, these bones and so on in our legs or sometimes in arms and so on. So, what are the issues basically in this talk? Basically, we will be talking about few kind of issues, which one of them is the wear, and then is corrosion, and there are some biological issues. So when we talk about any biomaterial, we usually uh, kind of are asked about these questions. So whenever you design any biomaterial, people will ask you how would it kind of perform in corrosive environments, because we all know that human body is highly corrosive. So and most of the time almost all materials are prone to some kind of corrosive uh, kind of these corrosive reactions. So people will ask you, so that is why we have to take care of this corrosion aspect. It is prominent both for permanent implants as well as temporary implants. So our intention is that we can control the corrosion rates. Of course, you can't eliminate the corrosion of your bioimplants, but then our intention as an engineer is to kind of control the corrosion rates. Um, because if you're not going to kind of control this, not only that you are going to weaken your bioimplant in due course of time, but at the same time you will be causing some of the problems in terms of some ions which are entering our body due to corrosion of these bioimplants, which can further cause some kind of diseases like Alzheimer's, neuropathy, and so on. Another issue is wear. So wear basically happens whenever we have some sliding contacts your relative motions between two components of any biome plant. So again, a lot of damaging effects you can see here. The materials basically physically they get into small debris which will go into the body. They will create problems. Not only that, they can also make our biome plants lose their tolerances, and they can get loosened and so on. And of course, another issue which is very important is biocompatibility issues. Whenever you design any material, so whether your material is biocompatible with the body or not, that's also biggest kind of question which everybody has to answer whenever we talk about new materials and so on. And in that space, when we say, because we are basically manufacturer, engineering people, so people talk about that, what are the methods to fabricate or you manufacture these bioplants. So traditionally, lot of load bearing bioplants, as you see, typically they are basically they have the base material and which are then coated, or their surfaces are modified, because this corrosion, wear, and even some of the biocompatibility issues, they are basically surface phenomenon, right? So approach usually is that we can make some cheaper base material, and then we can add our coating on it, which could be some high performance material. So base materials, of course, right from casting simple approaches, people are making these kind of bioplants. But now there is a lot of trend in terms of having additive manufacturing technologies also to build these bioplants, which we all understand that this additive manufacturer is basically they are big enablers for having very customized kind of bioplants. So that's why there is a lot of trend. Those who want to start or research work, it's a good area to work in, to use additive manufacturing to make some very kind of customized geometries or customized kind of bioimplants for different patients and so on. And when we talk about the materials, biomaterials for base manufacturing should be cheaper and should have a good mechanical properties. And usually, if you see the literature, you will see that a lot of people have used or commercially have been used are stainless steel, cobalt, chromium alloys, titanium and its alloys, and so on. And everything comes with some price. So as we go from stainless steel to titanium and so on, our cost considerations become more intensive, and you have to spend more money and so on. So this is some of the materials, and of course, lot more has been now proposed under investigation. But at least these are commercially available materials which are being used. I would say in the commercial bioplants, these are the materials which are being currently used. When we talk about surface modification, as I told you that the major issue or many of the issues of biome plants can be resolved if you can modify the surface of those biome plants. So in that vein, again, it's a very active area. Lot of techniques, lot of processes have been used to modify the surfaces of these biome plants. But then the question is that what should be the properties of the materials which you will use as the coating? So among that, one, obviously we would look for good mechanical strength of the coatings. They should be chemical and biological properties. For example, they should be highly corrosive resistant. Of course, for mechanical, why we need good mechanical strength? Because we want to take some load as well as wear resistance. We will understand that wear resistance is directly proportional to some of the mechanical properties and then biological properties as well, because the surface properties also affect this integration of your uh, body organs with the bioimplants. So when we talk about these materials for coatings, um, HA is most frequently, this hydroxyapatite is the most commonly used biomaterial which is being considered so far. So, in fact, this has approved plasma spray HA coatings for bioimplant surface modification. I'm talking here about especially the load-bearing bioimplants in my talk. Of course, there are some other instances, but majorly, if you see this almost plasma spray HA coatings are almost benchmark for these bioimplants, load-bearing applications like so. When we talk about surface modification routes, which are being explored for bioimplants, there is a lot of kind of routes by which people have tried. If you see the literature, people have used several technologies to modify the surfaces, right from the physical mode routes, what they call, then chemical processing, chemical routes, and then mechanical routes. In physical routes, we have this thermal spray, PVDs, ion implantation, and in chemical route, we have this chemical vapor deposition, sol gel deposition, electrochemical treatment, and so on. And in mechanical routes, we have manufacturings and so on. So, I mean, what I want to say here is that a lot of techniques have been tried to modify the surfaces of bioimplants to get these desired properties, which you talked a few slides ago. That means about this corrosion properties or wear resistance and biocompatibility, biocompatibility and so on. So today, what we are going to talk is mainly on thermal spray, and in fact, in that thermal spray, which is a big family again, where we have a lot of further technologies like detonation gun spray, electric arc spray, high velocity oxy-fuel, high velocity air fuel, flame and plasma, and so on. So here, our focus obviously will be on cold spray today, but this plasma is of course being uh, all commercially available right now. What is the problem with the plasma? When the problem with plasma is that we are basically using very high thermal energy to deposit the coatings. If you see this typical plot between thermal energy and the kinetic energy, you can see here that these processes like plasma spray, flame spray, high velocity oxy-fuel, all these processes, they used more of your thermal energy. That means we work at higher temperatures, or the process temperatures are very high, so that these materials which are being deposited are either melted or partially melted. But this melting creates some problems. I'll show you some case studies also. But then we are basically exploring cold spray because it's a solid state process, right? So the role of temperature in cold spray has been minimal, whereas the deposition is being done through kinetic energy. So if you see this thermal energy is on this side and we have this kinetic energy on this side. So in thermal spray, one comment I want to make about thermal spray is that the coating deposition is basically done with the help of thermal energy and kinetic energy. Means we are imparting some temperature and velocity to the particles to get them deposited on the surfaces. Now, during this whole evolution of thermal spray, if you see the history for the last more than 100 years, people have tried to decrease the role of thermal energy and compensated it with the increase in kinetic energy. And that is where we have reached to this cold spray, where the role of temperature is almost minimal and the deposition is basically taking place through this kinetic energy route. I'll talk more about this in further slides. Anyway, this is a kind of literature. Uh, if you can see, all these lot of materials have been tried and investigated from a scientific point of view, and of course, a lot of coating materials have been tried. Lot of different types of surface modification technologies have been used, and their performance has been evaluated in corrosive environments or in topological contexts and so on. And I mean, what we have seen that there is a kind of need actually. So to look into these materials and enhance the you know properties of these materials, or we should have I should say better that we need to have better and better materials for these biomedical coatings. And this study which I'm going to show you is basically an attempt to propose an alternative to our most frequently considered material, which is HAP, hydroxyapatite. But one of the major challenges with hydroxyapatite is the mechanical strength. Those who are working in this area must be knowing that one of the challenges which we face with hydroxyapatite is its mechanical strength. Right? So although it's very good in terms of biocompatibility and other properties, even corrosion resistance is very good. But then very recently there was an attempt to use a very similar material, which is again mainly calcium based material, which they call bagtite, actually BAG. So this bagtite has been considered recently with a possible or potential to replace the hydroxyapatite to kind of remove the limitation of mechanical strength, because bagdite has zirconium in it, which gives bagdite some kind of mechanical strength in addition to biocompatibility. But then the challenge is that how to deposit this material efficiently, and that is where this case study has been done. That whether first question is what are the challenges to kind of deposit this baghdad based materials, what will be the issues when we will be depositing them with the cold spray. That is one thing. And secondly, obviously to find out how they are performing against or vis the benchmark HAP coatings. So that is the motivation behind this study. I mean, technical or scientific motivation behind this study. So a little bit about cold spray, although I keep on talking about, I think some of you might already listened about this, but let me spend few minutes on the technology, right? That what exactly is the cold spray technology? So here, as I told you that in cold spray, the deposition basically helps. Sorry, just a minute. Let me find the cursor. So basically, in cold spray, we are using kinetic energy to propel the particles. So this is the substrate. Substrate is the material at which we want to deposit the materials. And these are the materials to be deposited. For example, your bag particles. So the feedstock material in cold spray is powder of any, say, kind of metal or composite or so on. Those particles are propelled at supersonic velocities. Now, how to propel these particles to supersonic velocity? We must have some logistics, and that is where we use this supersonic nozzle. And supersonic nozzles are, we all understand that it's if you want to accelerate of say gas to supersonic velocities, you will have to have this kind of convergent divergent nozzle to which you can accelerate your uh, gases to supersonic velocities. And that's what exactly we do in cold spray. We usually use nitrogen, helium, or air gas, which is heated and then propelled through this nozzle to supersonic velocity. At the same time, we also introduce powder particles in the jet of in that supersonic jet of gas, and obviously these particles are getting accelerated, or they will achieve the momentum. I mean, by momentum transfer from the gas to the particles will also achieve supersonic velocities. and then they will impinge on the surface and they will get deposited here. I'll go to this later, but let's go here. So two things we do: we heat the gas to certain temperatures. Why we heat? Well, somebody may argue that if it's a cold spray, why at all we are heating the gas? So basically, this gas is heated mainly to kind of achieve higher velocities, because our intention in cold spray is to achieve higher and higher velocities. And if you are not heating the gas, we all know that when it will throttle at the throat of this convergent divergent nozzle, the temperature of the gas will also go down and it will become heavier, right? So heavier means lesser velocity it will achieve. So what we do, we basically heat the material, sorry, gas, so that there is less cooling at this throttling process, or when we are in the this diverging section. So that helps us to achieve the supersonic velocities or higher velocities, okay, in comparison to what you can achieve in, say, gases at room temperature and so on. At the same time, some of this temperature is picked up by the particles and they also get softened, and this helps. But one thing is very clear, that the temperature of the particles never go beyond recrystallization temperature of the material of the powder. Sorry. So that means that's why we are calling it a solid state deposition technology, right? Now the question comes then, if the particles are not heated or melted, how they are getting deposited on this substrate, okay? And that is where we can understand this from this simulation done by one of my students, Vinay. So it says a single particle impact. Now he has simulated this particle. So this particle is basically, initially it is spherical and it's impinging on the substrate. So this is your substrate and this is your particle, right? So it is coming and striking with the supersonic velocity on this surface. Now as soon as you see here, this particle is interacting with this surface, what you can see here, there's a lot of plastic deformation happening, okay? And depending on the nature of these two materials, either both of these materials, both materials, when I say, means substrate material and the powder part material, both can deform, or one of them can deform, and so on, depending on what kind of materials combination we have, right? But right now here we can see that both the particle, both the substrate as well as the particle, both are plastically deforming, and this deformation takes in the matter of microseconds, because we are impinging the particles at supersonic velocity. So one thing is happening, lot of plastic deformation is happening. Now where we get this energy from? This energy is basically coming from this kinetic energy, right? This whole kinetic energy is getting converted mainly into this deformation energy. But another thing which is happening here is that people have a lot of interesting discussion in the literature, that how these bonding actually take place. And one of the major or most accepted kind of theory is what they call adiabatic shear instability theory, which says that when the particle interacts, the deformation is happening. One thing, another thing which happens here is the sudden rise in temperature. If you see the vicinity of the contact point between the substrate material and the powder material, you can see the temperature is rising all of a sudden at this contact zone, right? And this temperature basically leads to softening at the the interface. Okay, the material in the vicinity of this interface gets softened, such a condition that it loses its shear strength all of a sudden, and it then kind of undergoes this kind of strain, okay, severe strain, which helps you to kind of melt these points, these interface, and something happens, some which we call jetting kind of phenomena happens here. Okay, so this jetting happens if you see this picture, and this helps to pin the particle onto the substrate very firmly. So this kind of phenomenon, what they call is jetting, is very important to uh, s- kind of stick the material powder particle onto any substrate. Okay. Now this is something the theory which has been most accepted. Okay. Although there are some few theories, I'll comment on that also. But then another question comes is that we can discuss here with the help of this wonderful plot which shows the uh, role of the velocity actually in more systematic manner. So on this axis we have material deposition or deposition efficiency. So basically deposition efficiency is, you can understand it like that, that if I am impinging 1 kg of powder onto the substrate, so how much out of that 1 kg powder is getting kind of deposited on the surface, because there will always be some kind of rebound and so on. Okay, so for example, if we say 900 gram powder is deposited on the substrate, so uh, our deposition efficiency will be like 90%, right? Now this is one thing, and obviously as an engineer we would like to achieve as maximum as possible the deposition uh, um, efficiency. But then what is the restricting point here? Restricting point here is the this critical velocity or the velocity of the particle. And you can see here on this axis we have the velocity. As the velocity is getting increased, what you see here in this region, there is no deposition happening in this white region. Particles are simply going, but still they don't have the enough kinetic energy to do this kind of deformation. Okay, and also this kind of jetting phenomenon. Okay, so but as you keep on increasing the velocity, you reach to some point where the particles will start sticking to the surface, of course, but still they will be posting, or the deposition efficiency will be too low, and there will not be a condition of I would say very high adherence strength here in this case. Okay, still jetting has not take place, but particles has kind of stuck on the surface. But if you keep on increasing the velocity, you can reach to certain conditions where you will achieve this condition which we have discussed just now, which we call jetting phenomenon. Now here the deposition efficiency also gets increased, almost 100% he is showing here, maybe 1995 or something of that sort. Okay, but and of course this is our dream for any set of materials. I mean, when I say set of materials, means substrate and the powder particle materials. So this is our ultimate aim, but it's not that if you keep on increasing the velocity, you will get the benefits. At a point when you further increase the velocity, you will be again kind of decreasing the deposition efficiency. Why? Because once the particle velocity goes beyond certain limits, what you do, you basically end up doing the erosion of the substrate and the powder particle, this kind of situation, which is also not good, and our deposition efficiency will go down. So ideally we are looking for these kind of conditions where we can deposit more and more material to get a better DE values. Now another notice you can see here is the ductile materials, and here are the brittle materials. So this curve is basically for ductile materials, and we can all understand that ductile material only can deform. And if you see the brittle materials here, there's no deposition at all. Rather, they are in the negative regime of this plot, right? That means no deposition in case of brittle materials. Okay, why? Because brittle materials, they don't deform, and our cold spray, now we have understood that it's a plastic deformation waste process, right? So this remains still a challenge. A lot of people are trying to do coatings of brittle materials, standalone brittle materials, but not much success. And still, it's an open question for our future researchers how to tackle it. Of course, there is some success, but a lot more has to be done in this space. Anyway, this is more about thermal cold spray bonding issues. As I told you, lot of discussion, interesting discussion you can see in the literature. People have given different theories, how the particles are getting stuck on the surface, and but the most famous theory is from Asadi et al. They have their adiabatic shear instability theory, which I just elaborated in the last slide, has been well accepted. Right? This is further explanations of that theory, jetting theory. So basically, this is more kind of more simulation. One of the major problems in cold spray is that this process is so fast that you can't capture it experimentally. Right? It happens in less than microseconds. This deposition of each particle. That's why simulation. Those who work in simulation, they keep on simulating these behaviors, and from there they get these kind of interesting kind of understanding about the bonding mechanisms. Hydrodynamic plasticity is another. This was also given by another group. They were insisting that it's not necessary to have this kind of what they call softening at the interface. They say it's not needed. In fact, the kinetic energy itself is so much sufficient to create a hydrodynamic pressure on the particle to get deformed and stuck on the surface, right? And so on. But let's not go into that. This is hydrodynamic plasticity, the other theory. This is Sunny Gangraj group, which I just talked about. But anyway, coming back to our biome plant issue. So when we started this work, we were not having much data on, in fact, cold spray of even hair material itself, right? But we can see one of the interesting work where people have this group has basically compared three processes to deposit hydroxyapatite. This is by atmospheric plasma spray. This is by high velocity oxyfuel spray, and this is the cold spray, right? And here, what we saw was that we got some kind of benefit, and that benefit was basically retention of degree of crystallinity in the coatings. See, as I told you earlier, the temperature in atmospheric plasma spray or high velocity oxy-fuel spray basically plays with the chemistry of the HAP also. So you get your powder changes. It loses its crystallinity, right? So it tends to become more and more amorphous, right? Which is not good for this cell propagation and differentiation. Okay, so that is why this one, and why it happened, because we have low process temperatures, and which helps to retain the crystallinity in the hair. So that is one that was one kind of motivation for us, that we should also try cold spray to get benefits for our material, which is bag in this case. Of course, this is the system which we used at IIT Ropar. This is a national facility, as Dr. Sidhu was also indicating in my introduction. So this is a very state of the art, I would say. This can go up to 50 bar pressures and gas temperatures up to 1000 Celsius. So this means that this facility can be used to deposit coatings over diverse range of materials. Okay. So in fact, you are also free to use this facility if you guys are doing some kind of research in this domain. Another issue, of course, when we were trying to deposit this material, so as I told you, the challenge is there, right? So one of the another interesting question in the cold spray community is that what should be the surface condition of the substrate before we deposit the coatings on them, right? So there is again a good amount of debate. Some people have seen that it's good to have rougher surfaces before you do your coating. But on the other side, we people have shown that polished surfaces are good, right? And if you see, if you dig down, go into this literature, you will see that people have achieved success in both the conditions. But one thing is changing, that means material is changing, and of course, the nature of the interacting surface is also changing, right? So, but still there was, because another problem is that cold spray is relatively new and we don't have much database on that. So the point was that what should we do, right? What should be the condition of our samples when we are depositing the coatings? So that was the major question which has been resolved in this study also. Anyway, these are the objectives of this study. We will understand as we go, and this is the methodology. Anyway, we can skip it. So to resolve this first question, that what could be the surface condition, okay, for these composite coatings when we are using the cold spray, whether we should have rougher surfaces or we should have smoother surfaces, right? So that question was with the help of the titanium and titanium oxide composite powder, right? So we prepared this composite powder and we start doing certain experiments with cold spray by varying the surface condition, right? So of course, in all these studies, we have used this stainless 31 SS316L steel in this whole study because we wanted to use some cheaper kind of substrate material and then deposit some high value material on it, right? Or high performing material on it, right? So this part of the study is basically get the uh, insights on what will be the good surface preparation strategy for cold spraying of our powders. Now here, Avnish used three conditions. Um, in one case, it was as received, so we didn't polish the surface. Whatever roughness values was having on the surface of the steel, we used it. It's approximately 5 micron, and then we semi-polished it. Okay, simply we polished it with emery papers up to 800 grit size, and to reduce its RA value to 0.3 or something like that. And then we mirror polished also. So now we have three surface conditions, and then he tried to deposit the material under three different conditions. So here are the results. Okay, so this is basically as received surface. This is semi-polished, and this is the fully polished, or you can call mirror polished surface here. And you can see the difference. If you see the interface is intact in this case, whereas we don't have much good adherence in this case, neither in this case. So one thing was that our materials was supporting or giving good properties when we were having mirror polished. Even obviously, um, when you will do PhD, you have to go much deeper. Not only bulk coating, but then Avnish tried single particle impact study also to further kind of establish which uh, kind of condition is good. So here what you saw is this. This is a single particle impact. This is the surface picture from the top when the particle impinges, deforms on the surface, right? How it looks from the surface or top view. But here is the cross sectional view. So this is our as spray condition, or sorry, as received uh, substrate condition. You can see the loose adherence here. There's a gap, right? Here also we have some kind of discontinuity, but see the here, this is the mirror polished surface. So in this mirror polished surface, you can see very nice contact between this one, right? And this is again, these are the previous three figure just for your comparison. So this basically helped us to establish that it would be good if we go with the mirror polished surface for our further coatings, right? Of course, I can talk about why it is happening, because as soon as we have more rougher surfaces, our lot of energy goes into, because we are coming with certain kinetic energy, right? So some of that is basically going into deforming the surfaces, right? Um, or those hills on the surface, right? So this whole energy is not getting into kind of converted into deformation energy and so on. These are further establishments. In fact, you have to quantify the adherence strength in terms of scratch test. So here again, it is established that our mirror pulse sample is giving better adherence. Okay, and of course you can analyze those fractures to further getting the kind of understanding that which surface is having better scratch resistance and so on. So this is what is that in the first phase, Avnish could establish that okay, we need to have mirror post surfaces for having better coatings. So that is where then he started with Baghdad coatings. Now in Baghdad, the question was then uh, that how much Baghdad we should use, right, in titanium. One thing is that if you ask me that why not 100% Baghdad, we will not be able to do it with cold spray because cold spray, as we have just understood, Baghdad is a ceramic material, right? It will not deform, right? So, uh, and in my opinion, even if you do it, it will not have great mechanical strength, especially when you have sliding contacts and so on. So it's advisable that we use some kind of binder into it, and we use titanium in our study, right? These are some of the properties of Baghdad. So Baghdad, as I told you, it has a good mechanical properties as compared to our hat. Okay, and this could be a good when we are talking about say sliding contacts and or where we have direct kind of interaction between two surfaces and so on. So and this is attributed mainly that we have zirconium in our this Baghdad, which is not there in HAP. But otherwise, biocompatibility and other properties HAP and BAG are very similar. Okay, and that's why people are trying to use it. So here, so then our approach was that let us try to see how much bag diet we should use in titanium binder. Right? So he went up to 25% of this bag material, right from 10% to 25%, and then he deposited these coatings. Okay, so you can see all these four coatings. One thing is very clear that we could deposit the coatings in all the four cases, but then we have to evaluate them, right? So how they are performing in the it's not that you deposited something and you can give it, but you have to establish for its intended properties, right? So this is the characterization. One thing is these plots basically are showing that as we are increasing the Baghdad content in the coating, right? This is 10%, 15%, 20, and 25. Porosity of the coatings is increased, kind of increasing. This is the curve for porosity, and this is for coating thickness. So porosity is increasing. We can well understand that as the Baghdad, which is ceramic content, is increasing in a coating, and binder contact is decreasing, So one can anticipate this condition, right? Because porosity will be plugged once we have very well deformed adherent substrates or deformed particles filling all the gaps. But now we are increasing the ceramic content, and obviously there will be more spaces in the coating microstructure. Another thing which happens is that the coating thickness which could be achieved was also getting decreased as we were increasing the bag content in the coating, right? This is also quite understandable that as soon as we are increasing more and ceramic content in the coating, so ceramic deposition becomes difficult, and after certain layers, uh, you know, um, the layers will be much harder, and the formation levels will be decreased, and you will not be able to achieve thickness, higher thicknesses or better thicknesses than what you can achieve with lesser bag content, right? And this is about the roughness levels. Of course, RA value is increasing as we increase the bag diet. Same condition that now we have more ceramic uh, particles which are loosely packed in the coating, right? And so on. These are further kind of you know whenever you develop some coating, you have to establish the presence of those whatever you claim, right? So here we are claiming that we have titanium and we have bag diet, right? So that has been established through this map, right? That yes, in our coating we both have titanium as well as some elements of our bag, right? So which are present, and we could establish that. And of course, phase analysis through XRD and so on. The intention is again that whether whatever you're doing, uh, whether your process is allowing you to coating process is allowing you to retain the phases or not, right? So which is quite okay. We could retain the phases, and which is not surprising because we are doing it at a almost solid state condition, right? This is what being done to establish or to check the behavior of these in simulated body fluid environments. In other words, what they call in vitro corrosion studies, right? So this is being usually done with this electrochemical setups. So here are the results. Okay, so these are typical table plots. Okay, voltage versus current, corrosion currents and so on. So what you can see here is that, in fact, it was again an extensive study. Nish did it for longer immersion times. Even he went up to 40 hours of immersion time in ringer solution. Ringer solution is very similar to our body kind of environments. So here you can see that one trend obviously we could see in our coatings was that as the fraction of bag was increased, the corrosion resistance was getting increased. Okay, and that is very much visible in our results. Okay, so in other words, the more is the bag content, better is the coating is having um, corrosion resistance at least, right? These are all kind of further post-mortem analysis of our coatings. So once you corrode anything, obviously you have to see the oxide layers, how they look from the top, I mean, from the surface as well as from the cross section and so on. What are the compositions and of these oxide layers and so on. So this is all is being done obviously in this study also, and and of course it gives you some idea about the morphology of these oxide layers also. Okay, so oxide layers, um, whether they are very porous or whether there are some pits and so on. So all those issues you can resolve. In fact, everybody should do this post-mortem whenever they do these kind of studies. Um, of course, some further kind of this is basically not corroded here. This is basically as separate coating, and this is corroded, right? This is after corrosion, what has happened. Okay, so here even you can map the element distribution in these corrosion scales and so on, right? To oxygen is very important to see, uh, and this all you can get an idea about. Even you can do this phase analysis also through XRD to establish what kind of phases have been formed in the coatings after corrosion. So here, this is the phase analysis of the corroded coating samples. So you can see some of the phases which have been developed here. Most of these are kind of protective, right? So calcium oxide, zirconium oxide, and silicon oxide, titanium oxide. These are basically protective oxides, okay, which have been seen in the coatings as well. Then the one thing we have seen that as we are increasing the bag content, we are getting benefits in terms of corrosion resistance. But then what about the wear resistance, right? So here are the results. So here you see this plot little bit complicated, I can say that. But here you see this is the percentage of the bag content. This not 5%, but this is the substrate. This is 10%, 15%, and this one, right? Now this plot is basically showing the first data is this blue one is the micro hardness. So micro hardness, you can see the micro hardness of the coating is first increasing as we increase the bag content, but then it loses. The micro hardness is getting decreased here. As we are increasing the bag content, our micro hardness is getting decreased. This is again, loose packing of the part. As we are increasing the bag content, the cohesion between the interlayers of or the layers of the coating is getting compensated or compromised, right? And we are not getting a very dense and hence lesser micro hardness values. But this seems good here, that up to 15% we are getting good micro hardness. And we all know that this wear arcade equations and so on, that hardness is one of the major characteristics or properties which influence the wear behaviors, right? So then he conducted this wear behavior also under sliding contact conditions for these coatings, all these coatings. Okay, but then he used two strategies. In one case, he did this wear testing in dry condition, and in the second case, he did the wear rate analysis in the Hank solution. Hank solution is basically simulated body fluid. Okay, so here are the results. You can see this wear rate in the dry condition. Again, minimum wear resistance, maximum wear resistance has been shown by 15%. Okay, and also in the Hank solution. Okay, you can see this 15% is performing the best. Okay, so that is something which gives us that if we talk about wear resistance of these coatings, our 15% composition is best. Okay, whereas if we are talking about corrosion resistance, so we can have 25% of bag also. So what could be the lesson from this? The lesson could be that we can kind of have a recipe now, that if you are going to use or at the locations of your say biome plant where there are some kind of sliding contents, probably you should go for 15% bag, because this will give you very good kind of wear resistance, which will be the prime kind of requirement. Okay, but if you don't have any kind of sliding content, or simply you are placing the or the locations of your biome plant which are not kind of undergoing any kind of tribological contents, you can think about having better uh, uh, section of your bag. Okay, and this is possible in coating technologies. You can always have differential kind of compositions along the biome plants and so on. These are further again post-mortem. Basically, to understand, those who do work in tribology, they would like to understand what are the major mechanisms or signatures which we see in our coatings or in our sample which is being borne out under the given conditions. So that's what he has also done. So these kind of this is for say 10% bag coating, this is 20, sorry 15, and then go on. If you see here the damage, this is our best performing coating. The damage is much lesser here as compared to these three cases. You can see visibly as well from this micrograph, right? This is, and of course, this is a in Hank solution condition, right? This is under dry condition, dry sliding conditions. This is under Hank solution. Here again, you can see our best coating has a better kind of integrity and so on. There are further elaborations. People would like to analyze the counter disk also, right? And because this also gives a lot of information. Whatever debris you produce or you end up having on the counter disk, right, during wear pin on disk tests, okay, that also gives you some kind of information that what has gone uh, to your coating, right? Because some of the coating material can get and come on the counter disk and get deposited over there and so on. Those kind of tribofilms can generate and so on. But anyway, these are this thing. The last aspect of these coatings, deposited coatings, in as separate condition was obviously to do this biocompatibility analysis, which I think Manish did with one of my colleague in biomedical department. So they did it. I'm not an expert in these things, but they did these cell population, cell viability studies under these conditions. So what here we have seen that more is the bag content, better it is for our cell viability, right? But this 70% is usually the yardstick uh, for our, these qualification for biocompatibility for bioimplants. So this 70% threshold, anyway, all these three or four compositions are crossing. So that way, it's good news that these coatings are biocompatible, all of them, and so on. Anyway, these are the conclusion. I think we have talked about it. Okay, so then then we didn't stop here. Avnish wanted to have some kind of post processing of these cold spray coatings also. What is the need actually? The need is that can we further enhance the corrosion as well as wear resistance of these coatings, right? So is there any strategy? So laser, it's a generic remark that there is a lot of now kind of scope or potential to use the laser assisted cold spray, right? People are trying to use laser heat for several reasons. We can classify them that before coating. In before coating strategies, they are trying to, prepare the surface of the substrate for better adherence of the coating. You might have learned about these laser texturing and so on. So they will texture the surfaces, they will condition the surfaces to have very nice deposition, okay, by cold spray, right? So laser can be used there also. Laser has been used during the process also to supplement the heat, okay, in a controlled manner, right? So there also people are using in process I mean, they are using hybrid process, which is laser assisted cold spray, and even some people are using laser for post processing of the coatings as well, right? So in this case, our intention was that can we enhance the corrosion properties, right? And of course, what would happen to the wear resistance of the coatings? Now, one thing we have to understand that the porosity is there. I showed you some plots. There was porosity in the coating, right? So the idea here was that can we work out some laser process parameters by which we can, process the layers or at least upper layers of the coating to plug the porosity. And we know that if you can plug the porosity, you can enhance the corrosion resistance, right? That is as simple as that. So that is where, but then the challenge was what could be the parameters, okay? And there he took some kind of recommendations from literature, but then he did a lot of experiments uh, to play or laser processing at different powers, scanning speeds, and beam diameters. And he tried these different uh, combinations of these parameters to arrive at the some of the workable or best parameters, we should say, right? And of course, he measured these temperatures also in the process. Why temperature? Because this temperature will also dictate whether you are just kind of plugging them or there is recrystallization also in the coatings and so on, right? So, for example, here one coating he has shown 15%, I suppose. So when he did this laser uh, treat or treatment, so what we saw that even there was a differential in the microstructure of the coating along the thickness. Okay, so microstructures were different at the say outer layers, and they were different in here and they were here, right? So in other words, temperature was enough to kind of recrystallize the upper layers, okay, but we know the heat content will be lower as we go down. And I mean, one lesson is that when you are doing laser treatment, uh, your microstructures are also prone to get uh, kind of recrystallized and so on, okay. And that's what, but that's one thing, recrystallization. But in terms of change in um, these phases, the phase change was not prominent in these cases, right? So these are further, more kind of detailed micrographs of our all the four cases. So he did laser processing of 10%, 15%, 20%, and only 5%. All four he tried. Okay, and then obviously he wanted to see whether then uh, we are not compromising with bag and so on, right? So he could establish all these things and also the adherence issues and so on. Here are some of the results. For example, we were telling that porosity we want to tailor or we want to reduce it. So here you can see this is the red line is basically for laser treated cases. This black one is for the as sprayed coating, right? So in this as sprayed coatings, the porosity was obviously higher, right? And when we laser treated it, we could see that the porosity has decreased, and obviously this is going to help us. Not only that, even our surface become more of a kind of what you call finer. Its RA values they get decreased, Okay, and obviously now we are consolidating our coatings, right, with certain heat. So essentially we are filling the gaps and so on. So you can always expect that the surface will be smoother once you do it with the laser treatment. These are the corrosion just results, again table plots and so on. And no wonders, obviously you can see that the corrosion current density and all that, our corrosion resistance has improved in the laser remelted coatings. Okay, this should not be surprising, obviously, because we are plugging the porosity and so on, right? This is just an attempt to say um, what we call corrosion mechanisms or mode of corrosion in our investigated materials. So this is a bare steel, which is 316L steel. So when we do its corrosion, you can see this large bits and so on, ions being moving into the body and so on, or in the solution in this case. And you could see the non-protective oxide layers on this, right? So this is for bare one. So this is for coated steels. Okay. So if in the coated steels, of course, we have improved the corrosion resistance. Okay. And the mechanism is that we have nuclei and then they are spreading. These protective oxides are basically spreading over the surface, but still there is some scope for penetration of the corroding species to the subsequent layers and so on. But still our condition is better than this one. But then if we have laser treated cold spray coating, so essentially when you are doing this heat treatment by laser on the upper layers, you are consolidating the coating, you are plugging the porosity and so on. And we have seen that the titanium oxide layer growth is more preferential and more continuous on the surface, right? So, and obviously TIO is very good for corrosion resistance and so on. Then tribologic, then what about wear resistance and so on in these coatings? So here are the results. So here this one is basically showing us the micro hardness profiles for all the laser treated coating. Not here, but let me tell you because you will be interested what happened to the micro hardness after we did the laser treatment, right? So the after laser treatment, these micro hardness has improved actually. So especially at the top layers, and why it has improved? We can talk about 2-3 reasons. One is that recrystallization has been taking place because we have seen that the laser enough was in providing enough heat for recrystallization of the upper layers. So we have now fine grain microstructure, so which is giving us better micro hardness. And of course, we are consolidating also the material, right? So we are making the material more denser, which is expected to give a better micro hardness in the upper layers. So now attached to this obviously will be our wear distance, right? And of course coefficient of friction and all that, which you will evaluate through pen on disk, this one. Now here are the results. You can see this is 10%, this is 15% bag, this is 20%, 25%. These solid black curves are basically for as separate coatings, okay? But then after laser treatment, you can see there is further decrease in the wear rate, okay? And still this coating is best among all these 4 cases, but even its resistance has improved substantially once we have laser treated it. Okay, and you can correlate this with this micro hardness, right? Again, arcs be a question um, which is basically saying that if we have a good hardness, we can expect to have good wear resistance as well. Okay, so uh, this is again uh, a lesson that our laser treatment could be good strategy to improve upon the corrosion resistance as well as wear resistance in our coating. These are further kind of again post-mortem of our burnout surfaces, you know, to get into what kind of wear signatures we are kind of experiencing, right? So all these micro cutting and presence of these wear debris and so on, the lamination. These all features basically they indicate um, a lot of information about what could have gone, in terms of wear mechanisms. For example, this micro cutting and so on. Micro cutting is basically feature of the ductile materials, right? So that means in our case it should be a matrix titanium itself, right? Wear debris anyway embedment, and the lamination could be of our particle itself. Bag particle could have gone away and so on. Okay, but anyway, I think those who are doing gravology they would understand these things. But the point here is that your culmination of your wave study should not stop on these plots. Rather, it should go further into it to understand what are the mechanisms prevailing. And in that, these SEM micrographs, or you can call them factographs, they help us. Even these element mappings, they can tell us a lot in terms of transfer of material from disk to uh, pin or pin to disk and so on. And obviously, your studies should culminate on these kind of understandings in tribology. For example, here Amisha tried to understand the wear mechanism of coated and uncoated SS316L. Okay, in ring solution. So these are air spray coating, these are laser treated coating, right? So where what he wants to emphasize here is that these wear debris and the plastic deformation of the coating is much more, which has reduced after the laser treated coating. Okay, uh, and of course, let me tell you also that porosity, even in terms of wear resistance, is not also not great, because porosity acts as a kind of a point from where the cracks can go, and then two cracks from two locations can then uh, merge and give lots of chunks of weird debris and so on, right? So that's one. I think this is already I have spoken. This is like a conclusion. So what we have tried to talked about today is about these coatings, okay, and overall, what we have seen that we have some strategies. Cold spray can be used, of course. Then composition wise also, then we can have second step also in terms of laser treatment and so on, right? Last question was that what was it compared with the titanium HAP also, these titanium bag and titanium HAP, right? Because we started our whole story with the intention to replace HA, right? So this at least corrosion resistance we have compared. So he developed these coatings with cold spray, titanium 20% HAP as well as 20% bag, right? And here are the results. So this is HAP, this is bag. These are the values I core. So you can see we are on benefited side. Okay, and yeah, so in literature also he compared it with and so on. Okay, uh, I think I will stop here. These are more kind of things. So thank you very much for. I'm sorry, my um, throat is not great today, so I hope it makes sense. What
No,
we.
sir,
Thank you very
it's
much.
fine, sir. Uh, So informative session. So now I call participants. If you have any question, you can unmute your mic and ask the questions.
Yes. Good evening, sir.
Good evening.
Sir, my name is Sony Slot. I'm a research scholar under the guidance of Dr. Professor Shankar Sehgal, UIT, Punjab
Mhm.
University.
Mhm.
So, sir, my question is related to basically effect of heating. Effect of gas temperature which we are using on the deposition rate. Is there any significant or insignificant we can say that effect?
Deposition efficiency, it can hello.
Yes, sir. Yes, sir.
The gas temperature, as I told you. See, before that we should understand that for each set of materials, each set of interacting materials means substrate and the material to be coated, right? There is a critical
Yes,
velocity, right? And our intention should be to achieve that, right? So if you can achieve it at whatever gas pressure you can do it, it is good, right? But having said that, the gas temperature can slightly help us, right, in terms of softening the particles and hence to facilitate this kind of condition at lower this one, right? So
okay, sir.
not much significantly, it is not going to help you much, I should say, the temperature, but it will help us in terms of increasing the critical velocity for better deposition efficiencies, right?
Yes, sir. Yes, sir.
Now,
Yes, sir.
this temperature also helps, especially when we are having difficult to coat materials. For example, when we are depositing very harder materials, their gas help. Uh,
Hello, sir. Your
how
voice
much
is
you can soften these particles,
hello.
right? Hello. Hmm. Can you hear me now?
Yes, sir. Yes, sir. Yes, sir.
So
Now I can hear you.
in certain can yeah, in certain, I would say, let me not confuse you. In certain cases where we have hard materials or difficult to kind of deposit materials, right?
Yes, sir.
Their temperature can help you
Yes,
significantly.
sir.
But for
Yes.
softer materials, it may not be very much helpful, right?
So it
Yeah.
can we can say this on the basically effect on deposition rate. Simultaneously, we can say for other properties also, or we have to go in detail for that particular property.
See, that is the point where we have to come out. If you are increasing the temperature unnecessarily, right? So that the problem may come in terms of playing with the chemistry of the powder particle, right?
Ji. Yes, sir.
So that is another kind of threshold, right? So we should not go beyond, very much kind of very high uh, temperature. If you go very high temperature, then anyway you are entering into the regime of say high velocity oxy-fuel coatings and so on, right?
Yes, sir. Yes, sir. Yes,
So
that's why I'm
to
asking.
my understanding, the best thing is that we use this temperature to achieve the desired proper critical velocities for more deposition efficiency, right?
Yes, sir.
That role is very much critical. But and especially when we have these easy to play materials, there we need not to increase. For example, if you have aluminium and you are using it say 900 degrees Celsius temperature,
Yes, sir.
you will be playing with the chemistry of the aluminium particles,
Exactly,
right?
sir. Exactly, sir. Yes.
But on the other side, if you have a superalloy, maybe you should try more temperature, right? Because that's not going to hamper its metallurgy any case, right?
Exactly, sir.
It can help achieving good uh, this one critical velocity, hence the deposition efficiency, and temperature also is higher. That also helps to improve the bond strength and may
Exactly.
also contribute to your deposition efficiency indirectly, right?
Yes, sir.
Those kind of things I can, say right now.
Yes, sir. Thanks a lot, sir. Thanks a lot.
Thank you.
The parties. Okay. Sir, I have one question. I don't know it is relevant or
Yes.
not. That
Mhm.
is there is a effect of particle size on the deposition?
Yes, yes, it is there actually. Particle size will definitely affect it. There are again two, three insights. One thing is that we can't go away with the very fine particles, right? Because first logistic problem is there that you can't flow them, right? So that's where if you see the cold spray literature, people say start from say 20 micron, 25 micron to anything up to say 50, 55 micron, right? Ideal is 40, 45 micron. Because if you are going less than that, first thing is that you are unable to flow it properly through the nozzle, right? Secondly, since mass is very less, okay, the momentum transfer can also affect mb square, what half mb square, right? If mass is very less, your
Yes.
Sir, you are not audible.
Uh,
hello, can you hear me?
yes.
Yes.
Hello, can you hear me? Hello,
Yes, sir, you are audible now.
Yes, sir. Yes, sir.
Yes, sir. You are audible, sir.
hello.
Yes, sir. Voice is correct, sir. You are audible, sir. Yes.
Sir, we are hearing your voice.
Okay, you are hearing me. Okay, I was not hearing you actually. Anyway, so uh, so very kind of again, if we have a kind of very large particles, it will be difficult to get the again the higher critical velocities, right? So those kind of problems, right? So yes, particle size has an effect. Third comment I can make here is that in terms of microstructure of the coating also, if you have finer particles and if you can accelerate or if you can achieve those desired critical velocities, you can have better coating, uh, which will be more denser coating, right? So particle size lesser is good, but then how lesser that you should be able to avoid the non-flowability or agglomeration. Okay, that has to
Okay,
be
sir.
seen. And secondly, you should be able to achieve those critical velocities. And in that respect, smaller is better, right? If you can achieve these objectives, smaller is better to have very dense coating, right?
Correct, sir. Yes.
Sir, good evening. Am I audible?
Is it
Yes,
fine?
madam, you are audible.
Yes, audible.
Sir, good evening. Sir, I have one query. Like you have explained this biomaterial with respect to hard materials, this coating and surface modification. I have one question. Like I'm trying what I also
Actually,
doing.
I am unable to listen to you people.
Yes,
Oh.
audible, sir.
I am audible from, I think, yeah, I can't hear you people actually. That's the problem.
Okay. Sir, if you allow, I can write my question in the chat box also.
Yes, madam, please write your query in the chat box, and Dr. Sidhu is online with the expert, and he will pass on your query to Dr. Harpreet Singh.
Okay, okay. Thank you, sir. I'm writing. I'm writing.
Dr. Sidhu, can you hear me?
Second, I am hearing you.
Yes, Dr. Dr. will be writing her query in the chat box. So you please pass on the query to the resource person.
Yes, yes. Yeah, I will pass on, sir. Yes, Dr. Payal Gupta wrote the query that, sir, I have working on a soft material functionalized and modified with respect to the microbial colonization. So, can share your some insight on it?
Can you hear me, Dr. Sidhu? Can you hear me now?
Yes, yes, sir. Yes, sir, I am hearing, sir.
Okay, let me speak through this only.
Yeah. Medical skill. As I have Professor Harpreet asked me that Dr. Payal Gupta is working on a sort material, but this that the group of Professor Harpreet Singh is not working on sort materials, so she or he has to see some another alternative.
Lab. And neither these
Okay.
technologies are very good for depositing these kind of soft materials. Right?
Okay. Okay, sir. Any other? Okay. Correct. Any other question, please? So I think the queries are over. Sir, you have given a very good presentation. So from Hello.
Are there any questions?
No, sir. No, sir. No questions.
It's happening here. My internet connection is not great. Okay.
Sir, it's okay, sir. Everything.
Anyway, I invite people. If they have any questions, they can write to me. Right?
Okay, sir. So,
Okay, thank you very much. Thank you.
thank you, sir. So, I thanks Professor Harpreet Singh. So, thank you, sir, for sharing your invaluable insights and expertise with us today. Your lecture provides us with a wealth of knowledge and latest development on this important topic of surface engineering. So, we appreciate your time that you have invested in preparing and delivering this informative session. So, I also all the participants for their patience. So, Dr. Harpreet Singh has also written his email. So, if anyone wants to contact him, you can contact him through email. Yes. Hello. Hello, sir.
Okay, thank you, Dr. Sidhu. I think I can now log off. Right?
Yes, sir. Yes, sir. Please, sir.
Thank you, all the participants. Thank you.
Thank you, sir.
And thank you, Dr. Sahil, for conducting this course.
Thank you, sir.
I think organized with Dr. Sidhu. Thank you.
Thank you, sir.
Bye-bye. Bye-bye. Take care.
Bye, sir.
Okay, sir.
Okay.
Thank you, everyone.
So,
Sir, I am going to stop the recording.
yes, please.